Imagine pressing a rewind button on Earth. Not just a few years back, but 4.6 billion years into the past. Our planet's story is written not in books, but in rocks, fossils, mountains, and oceans. This is the geological history of Earth, a dramatic journey of fire, ice, collisions, extinctions, and rebirth. To understand this vast timeline, scientists divide Earth's history into eons, eras, periods, and epochs, like chapters in an epic book. Hadean Eon, 4.6 to 4.0 billion years ago. Formation of the Earth. The Hadean Eon represents the earliest stage of Earth's geological history. It extends from the formation of the Earth about 4.6 billion years ago to approximately 4.0 billion years ago. This eon is named after Hades, the Greek underworld, reflecting the extreme and hostile conditions that prevailed on the young planet. Origin of the Earth. Earth formed from a massive rotating cloud of gas and dust known as the solar nebula. Under the influence of gravity, material within this nebula began to accumulate. The Sun formed at the center, while smaller bodies called planetesimals collided and merged to form the planets. As Earth grew through continuous collisions, enormous amounts of heat were generated. This heat came from frequent meteorite impacts, gravitational compression, radioactive decay of elements. As a result, early Earth existed largely in a molten state. Differentiation of Earth's interior. During the Hadean Eon, Earth underwent planetary differentiation. Heavy elements such as iron and nickel sank toward the center, forming the core, while lighter materials rose upward to form the mantle and early crust. This internal layering laid the foundation for Earth's present-day structure. The giant impact and formation of the Moon. One of the most significant events of the Hadean Eon was a collision between Earth and a Mars-sized body, commonly referred to as Theia. This event is known as the giant impact hypothesis. The collision ejected vast amounts of debris into Earth's orbit, led to the formation of the Moon, remelted much of Earth's surface. This event played a crucial role in stabilizing Earth's rotation and influencing future tidal and climatic conditions. Development of the early crust. As Earth gradually cooled, a thin and unstable crust began to form. However, due to intense volcanic activity and frequent impacts, this crust was repeatedly destroyed and reformed. Direct rock evidence from this time is extremely rare. However, zircon crystals found in Western Australia, dated to about 4.4 billion years old, suggest that parts of Earth's surface had cooled sufficiently to support a solid crust relatively early. Presence of water on early Earth. Evidence from ancient zircon minerals indicates that liquid water may have existed on Earth during the late Hadean Eon. This suggests that oceans could have formed much earlier than previously believed. Water likely originated from volcanic outgassing, water-rich meteorites and comets. The presence of water was a critical factor in making Earth suitable for future life. Formation of the first atmosphere. Earth's earliest atmosphere developed mainly through volcanic activity. It consisted primarily of water vapor, carbon dioxide, methane, ammonia. There was no free oxygen in the atmosphere during the Hadean Eon. This atmosphere helped retain heat and allowed water to remain in liquid form despite the faint early sun. Scarcity of Hadean rocks. Very few rocks from the Hadean Eon have survived because Earth's surface was constantly reshaped by intense volcanism, meteorite bombardment, plate tectonic processes. As a result, scientists reconstruct the Hadean environment using indirect evidence, such as ancient minerals, meteorites, and lunar samples. Significance of the Hadean Eon. By the end of the Hadean Eon, Earth had developed a layered internal structure. A primitive crust had formed. Liquid water was likely present. A primary atmosphere had developed. These conditions prepared Earth for the Archean Eon, during which the first life forms would appear. Archean Eon, 4.0 to 2.5 billion years ago. The dawn of life. The Archean Eon marks one of the most important phases in Earth's geological history. Spanning from 4.0 to 2.5 billion years ago, this eon represents the time when Earth transformed from a hot, unstable planet into a world capable of supporting life. It is called the dawn of life because this is when the earliest known living organisms appeared. Environmental conditions of the Archean Earth. During the Archean Eon, Earth was still much hotter than it is today. Volcanic activity was widespread, and the planet's interior retained a large amount of heat from its formation. The atmosphere was anaerobic, meaning it lacked free oxygen. It consisted mainly of carbon dioxide, methane, ammonia, water vapor. Oceans were already present, but they were warmer and richer in dissolved minerals, especially iron. Formation of the first stable continents. One of the most significant geological developments of the Archean Eon was the formation of the first stable continental masses, known as cratons. These ancient crustal blocks form the core of present-day continents. Examples include the Indian Shield, the Canadian Shield, the African and Australian shields. The development of continents played a crucial role in stabilizing Earth's surface and creating diverse environments. Origin of life. The first living organisms. Life first appeared in the Archean oceans. These early life forms were simple, microscopic, single-celled, prokaryotic. They lacked a nucleus and complex structures. The earliest organisms were anaerobic bacteria that survived in oxygen-free environments. Cyanobacteria and photosynthesis. Among the most important life forms of the Archean Eon were cyanobacteria. These microorganisms developed the ability to carry out photosynthesis, using sunlight to produce food. In the process, they released oxygen as a byproduct. Over time, cyanobacteria formed layered structures called stromatolites, which are among the oldest fossil evidence of life on Earth. Though oxygen levels were initially very low, this process slowly began changing Earth's atmosphere. Banded iron formations, evidence of rising oxygen. As oxygen released by cyanobacteria entered the oceans, it reacted with dissolved iron. This chemical reaction led to the formation of banded iron formations, BIFs, distinct layers of iron-rich and silica-rich rocks. BIFs provide strong geological evidence that oxygen production had begun during the late Archean Eon. Climate and oceans. Despite the sun being weaker during this time, Earth remained warm due to high levels of greenhouse gases like carbon dioxide and methane. The oceans acted as cradles of early life, protecting it from intense ultraviolet radiation, which was stronger due to the absence of an ozone layer. Why Archean rocks are rare. Rocks from the Archean Eon are scarce because plate tectonics recycled much of the early crust. Continuous volcanism reshaped the surface. However, surviving Archean rocks are extremely valuable, as they provide insights into Earth's early environment and the origin of life. Significance of the Archean Eon. By the end of the Archean Eon, Earth had stable continents. Oceans were well established. Life had begun and diversified. Photosynthesis had started altering the atmosphere. These developments prepared Earth for the Proterozoic Eon, during which oxygen levels would rise dramatically and complex life would evolve. Proterozoic Eon, 2.5 billion to 541 million years ago. Oxygen changes everything. The Proterozoic Eon marks a revolutionary phase in Earth's geological and biological history. Extending from 2.5 billion to 541 million years ago, this eon represents the time when Earth's environment underwent fundamental chemical, climatic, and biological transformations. Most importantly, it was during the Proterozoic Eon that oxygen became a major component of Earth's atmosphere, permanently altering the course of life on the planet. A world before oxygen. At the beginning of the Proterozoic Eon, Earth's atmosphere still contained very little free oxygen. Life forms that existed at this time were mainly simple, single-celled organisms, similar to those of the late Archean eon. However, deep within the oceans, photosynthetic cyanobacteria continued producing oxygen, a slow but powerful process that would soon reshape Earth. The Great Oxygenation Event. One of the most significant events in Earth's history occurred during the early Proterozoic eon, the Great Oxygenation Event, GOE. As oxygen production increased, oxygen began accumulating in the oceans and atmosphere. Anaerobic organisms declined or went extinct. New oxygen-tolerant life forms emerged. This rise in oxygen transformed Earth from a reducing environment to an oxidizing one, making complex life possible. Formation of the ozone layer. As atmospheric oxygen increased, some of it formed ozone, O3, in the upper atmosphere. This resulted in the development of an ozone layer, which protected Earth's surface from harmful ultraviolet radiation. This protection was crucial. It allowed life to gradually expand beyond oceans and explore shallow waters and, eventually, land. Evolution of complex life. A major biological milestone of the Proterozoic eon was the emergence of eukaryotic cells, cells with a nucleus and complex internal structures. Later, multicellular organisms appeared. By the late Proterozoic, the oceans supported a variety of soft-bodied organisms, collectively known as the Ediacaran fauna. These organisms represent some of the earliest complex life forms in Earth's history. Proterozoic climate extremes, snowball Earth. The Proterozoic eon was also marked by dramatic climatic events. At several points, Earth experienced global-scale glaciations, often referred to as snowball Earth episodes. During these times, ice sheets covered most of the planet. Oceans may have frozen near the equator. Life survived in deep oceans and geothermal zones. These extreme events highlight Earth's dynamic climate system. Growth of continents and plate tectonics. During the Proterozoic eon, continental crust expanded significantly. Large landmasses collided to form early supercontinents, such as Columbia, Nuna, and later Rodinia. These tectonic movements influenced climate patterns, ocean circulation, evolution and distribution of life. Significance of the Proterozoic eon. By the end of the Proterozoic eon, oxygen became a stable part of the atmosphere. The ozone layer was established. Complex multicellular life had evolved. Continents were well developed. These changes prepared Earth for the next major phase, the Phanerozoic eon, which begins with the Cambrian explosion of life.